inspection, construction and road maintenance in outdoor settings, and building construction and tunnel construction in indoor settings. And I make this distinction because it's quite crucial for the technologies that need to be developed to provide such tools for the inspection use cases. Yes. I didn't check the sound of the of the videos. Sorry about that. So the idea of using these tools is basically to provide. We need repetitive inspections. We need safe inspection and also fast acquisition of data, especially to feed the digital twin in order to make the wisest decision in the process of construction in different environments. So as I mentioned, I will focus today on the, let's say, right-hand side, which is the indoor construction use cases. You will see basically the tunnel inspection, but this technology was also used for the building inspection in FIRA. The technology stack is basically the same, but I wanted to stress also the left part, which is the road construction and maintenance use cases, where navigation in open spaces is is solved today using satellite-based positioning. So our role there was more in the intelligence and the autonomy that the drone that determines what the drone is able to do. So we made accessible AI algorithms for onboard computation with onboard computational resources and for the detection and segmentation of different parts of the road, and also the construction of 3D models, which is also like you can actually buy that in a store to obtain these kind of products. So this had like from the scientific point of view had less interest for the scientific community. Actually, we were more focused. We devoted much more efforts in the indoor navigation scenarios. That's why I'm focusing mostly on that. Motivation for using these kind of tools to provide fast and safe data. Needless to say, the human risk that involves the blasting operation in tunnels. Not only human risk, but also economic impact, operational and social. And this provides huge advantages for carrying out these kind of operations. What are the main challenges of using aerial robots in these scenarios? Well, as I mentioned, if you are flying outdoors in open spaces, you pretty much can automate the missions without much problem. But when you are inside, even inside buildings, you cannot rely on the external positioning system for navigation, and you need something else. As I point out here, the absence of satellite-based signals prevent you from navigating safely. And especially in tunnels, not so much in buildings, especially in construction buildings, because there are things around, but in tunnels are typically straight and symmetrical structures. And also the lighting conditions may hinder successful localization techniques. And also in construction settings, dust and debris could prevent you from actually sensing the right things to sense in order to know where you are and know where you want to go with the platform. So what did we do? Given that there were no commercial platforms that provide all these capabilities, we came up with designing our own system, our prototype system that I brought with me. Is in one of the benches on the side. And the main, let's say, sensor is the thing that is on top. It's a 3D LiDAR that you may have also seen on top of autonomous cars. And this provides a 360-degree view of the surrounding of the platform, which is very convenient for these scenarios. We had some other helps with an altimeter and a gyro stabilized camera that initially was for the mission itself, so for scanning what's around it, and not for the navigation. But as I will explain later on, we also made good use of the infrared camera because it's also very convenient for solving the lighting problems inside tunnels or inside buildings that are not well lit at all in all the spaces. So as I said, we work in a combination of sensor data for achieving successful autonomous navigation, both the LiDAR, the 3D LiDAR on top, and also the cameras. But not only that, I mean, I'm focusing too much on the localization, but this is like the first stone that you need to build the whole thing. You need a safe obstacle detection to prevent bumping into obstacles, into walls or the ceiling. You need trajectory planning. You need exploration strategy. So there are a lot of things going on when the drone is actually flying. I have some videos of the full thing. So there are a lot of things going on while the drone is flying. This is 100% autonomous. You push a button, the drone takes off and then performs the exploration. This was in the Santa Barbara tunnels that we conducted last year. And as you can see, the colored point cloud on the right side is what the 3D LiDAR is seeing. And it's not really, you cannot really see very well, but there's like a straight line that is like a short-term path that indicates where the drone should be according to the exploration mission that we agreed. That was basically go forward until you reach the end of the tunnel, or you don't have enough battery to come back to the initial point, the takeoff point. So you can see that the drone every once in a while may stop a little bit. This is because of the adjustment of the safe area around it to prevent collision with obstacles. In this case, the walls, both walls and the ceiling. And well, basically, I think it's about to reach the end of the tunnel. There were people, as you can see in the shadows. There are some people following the drone. One of them recording. The other one is the safety pilot. The pilot is not intervening in this operation. He's only there for safety in case something happens. He can take over the control of the drone and land it safely. But thankfully, that was not the case most of the times. And now, once it reached the end of the tunnel, it's coming back. As even the video is accelerated, you can note that the speed of the drone is higher than while it was coming in the first place, because it takes advantage of the fact that the map is already built. It's not shown the full map in the right side, but in memory, I mean, it's loaded, so it can be it can go back faster than it came in the first place, thanks to this. This is a similar video, but I wanted to show also for stressing out the fact that the system, the same sensor suit, is suitable for less convenient environment or scenario conditions in terms of dust or smoke or fog. I mean, both the LiDAR and the infrared camera that the algorithms use for determining where the drone is, where the aerial robot is, and where it should go, are quite robust under these conditions. And this is an example of this. So this is basically the same operation, but with slightly worse conditions in the environment. This is very cool, but what is this for, actually? So the outcome of this mission is actually the map that you want to provide to the company that is exploiting this facility, and to make decisions in terms of what to do once there was an explosion, and what's the current state of the tunnel. So what we did was to compare the map that the actual UAV built during this operation of going back and forth that took less than 10 minutes, and compare it quantitatively with the map that was built using a total station that took 2 days for creation. And the average, I mean, we have some papers about these experiments. Actually, one of them was accepted very recently that we will be presenting next month. And the errors, depending on what you need to do, the errors are admissible. If you are looking for millimetric precision, obviously this is not the right tool, because for starters, the LiDAR has a precision of 3 to 5 centimeters. So you cannot expect to have better precision than that. But for other kind of operations, like big, let's say big things or bigger things than that, this was more than enough. And yeah, that was basically it. I wanted to stress that even though I focus almost my entire presentation in this use case, these tools are also very useful for other scenarios, not only the building, but also other indoor spaces. We have worked in factories for inventory management. I mean, this is the tool to do something else. And also outdoors, because for construction sites, for roads or for bridges, for other kind of scenarios, this could be a very valuable tool, relying or not on satellite-based signals. But this could provide a different point of view, safer and reaching less accessible places than with standard current tools, and posing above all, posing less risk to human workers. And that's basically it. Thank you.
Thank you, Francisco, for your presentation. Thank you. No, here. Grazie. So I would like to call on stage now Maria Teresa Lazzaro, Head of Robotics Research and Development Line at ITA. She will give us an overview of the ground robotics. Here's the, to change the slides. Thank you.
Okay, so thank you, everybody. So in this presentation, I'm going to show you the development regarding the autonomous wheel loader that ITA has done in collaboration with Hydromec, which is also a partner in the project. Here, the main motivation is it's related with one of the use cases in the project, which is the tunnel construction. We also participated in the road construction scenario, but as also Fran mentioned, this is the most challenging use case. So I have also focused the presentation on this use case. And here, well, the motivation is that, well, during the construction of the tunnel, there are frequent explosions that make, well, the atmosphere is unbreathable. Then the works must be stopped approximately 1 hour and a half. So because these are unsafe conditions for the workers. So the idea was to deploy autonomous machinery to start with the debris removal process during this time, to have a more efficient process. In particular, we have developed the autonomous wheel loader for the debris removal operations, and we have validated this use case in the facilities of Fundación Santa Bárbara here in León, in Spain. And well, the main challenge is not just the robotization itself of a machine of these characteristics, but also, as Fran mentioned, this is a very particular and challenging scenario. So it was very challenging to make this machine operate safely in the environment. So the first step was to perform the robotization of the machine. This is a commercial machine by Hydromec. So we have intervened the machine by including sensors to achieve a full 360 degrees perception. We equipped the machine with 3D LiDARs, radar that work better in dusty conditions. RGB and thermal cameras, and also GPS, so it can also work in outdoor scenarios. Also some onboard sensors like encoders and wheel speed sensors. So we are also able to estimate the machine's own state. And of course, we have also equipped a PC where our algorithms run, which connects directly with the ECU of the machine and also with external systems through Wi-Fi and 4G communication modules. After the robotization, then it comes the moment to start the development of the software. First, we have developed all the functionalities that are required to obtain a fully autonomous system, from the low-level control that allows us to control directly commands to the machine, like throttle and brake commands, also to steer the machine, so to achieve the desired velocity and linear and angular velocities. Other algorithms like pre-processing data, and then other autonomous functions, general autonomous functions involved in any autonomous system, like localization, mapping, navigation, obstacle avoidance, and other functions more specific to the tasks that the machine has to develop, which are the load and unload maneuvers. And then we have also developed an orchestrator, a mission planner that is in charge of activating the different processes in the correct moment during the execution of the complete task. Regarding the load and unloading maneuvers, we have defined a high-level strategy where basically these maneuvers are composed of a sequence of actions while we monitor certain values of the machine. So, for example, for the loading maneuver, we just approach the pile of material at a constant speed. Then when we start to measure the pressure in the cylinders from the bucket, we start a procedure to lift the arm and the bucket to take the material. And for the unloading, we also do a sequence of operations. In this case, we approach also the designated area and lift the bucket and the arm to deposit the material. Here we have to implement two different unloading strategies. One on a dumper, which is a more realistic case, and it's what we did in the tunnel of Santa Barbara. But also in our facilities at ITA, we decided, as we didn't have the dumper, we also prepare a strategy for unloading in a delimited area with the beacons that you can see in the image. But in the end, they work in the similar way. So once we have developed the algorithms, comes the moment to deploy the system in the tunnel. So the first step is to build the 3D map of the environment using the onboard sensors of the machine. And then we convert this 3D map into a 2D representation, which is suitable and compatible for the 2D navigation system of the machine. We select a set of waypoints that the machine has to reach and to follow until it reaches the excavation front. And as you can see also here in the video, the machine navigating autonomously in the tunnel. And then regarding the autonomous operations like loading and unloading operations, you can also see here some videos. Okay, no? The loading operation with using real debris extracted from previous explosions. We didn't do a real blasting in that moment, but we used the same debris that is producing other explosions. Then we have the exit maneuver, In this case, the machine was too big for the tunnel dimensions, so it had to exit the tunnel backwards, as it was no way of doing any kind of maneuver inside of the tunnel. And then the downloading on the damper, as we have seen in the video. So yeah, this was a brief presentation. To conclude this great work in the last 3 years, I put here a promotional video. I think as conclusions, we have robotized autonomous wheel loader and we have demonstrated its performance in real and challenging scenarios. Next, of course, this is still a prototype that has been developed within a European project. We would like to escalate this towards a commercial product together with Hydromec. And for this, we will need to evaluate the system in more complex scenarios over longer periods of time. We just were 5 days in the tunnel. It's not enough to validate a system like this, no? So we will need to have more extensive experimental setups, and we want also to improve the loading and unloading maneuvers to consider different types of pile of materials and also different damper types. And that's all. Thank you.
Thank you, Maria, for your presentation. We now have Ivan Villaverde from Tecnalia, which unfortunately was not able to join us physically here today with us. I think he's online. So, Ivan, can you hear us? Let's see if...
Yes.
In case we might need to...
Hello, David. Yes,
Hi, Ivan.
I'm here. Yes.
Nice to meet you. We can see you projected on the screen. They told me that you can start sharing your presentation via your screen if you want.
I'm going to share my screen now. I hope you are seeing it.
Yes, we can. The first slide, I think. It's full screen, so it seems to be fine. Thank you.
Okay, perfect. So I shall start, right?
Yes, please go on. Thank you.
Okay. Well, thank you, David, for the introduction. As he said, I'm Ivan Villaverde from Tecnalia. I'm a senior researcher there. Tecnalia is the largest private research and development center here in Spain. We do a lot of things, really, but I work on the flexible robotics group that we try to do things a bit more advanced with robots that are a bit beyond what they are used usually in industrial environments, in fixed environments. So regarding this project, that is a framework in the sorry, I don't know which is the key to pass. Because the focus is, sorry, okay, sorry for this technical problem. So we will start with a bit of context on this work. So have you already learned from previous presentations? This development is framed within the road maintenance application. In this case, the main objective was the integration of the AMR, among other technologies, into a digital twin-driven system for road maintenance management. The specific task that we wanted to achieve with this AMR was to measure the retroreflectivity of the horizontal road markings on the asphalt. So our objective was to develop a prototype AMR that is able to fulfill this role. So to achieve this objective, we have to implement a series of capabilities in the robot. brought from a hardware and software standpoint. And these capabilities are more or less what I'm showing here in this slide. So they include the integration with the digital twin itself for mission management and data exchange, integration of a retroreflectometer sensor to actually make the measurements of the ROAD signs, and the ability to operate autonomously in an outdoor road environment. And this capability also requires robust outdoor self-localization, autonomous navigation, and automatic detection of the road markings that we need to measure. So to achieve this level of autonomy, we need to integrate a lot of different sensors in the prototype that we were developing. So we started with a basic drive-by-wire platform, Planck, from the Chinese manufacturer Pixloop, that we will control through a CAN CIN interface. And in this platform, we integrated multiple components in a customized all-weather bodywork that you see here in the picture. So we integrated multiple sensors like 3D lidars for navigation, GPS and AIMU also for navigation, 2D lidars for safety, and also all the required communications equipment like 4G and internal CAN and Ethernet communications. The integration of the retroreflectometer was a bit more tricky, let's say, because for the characteristics of the device, and it was as fragile equipment, we had to integrate it in a liftable platform that you see there. It's a fully custom design, and we made custom ROS controllers for controlling it from the whole system. And also we developed custom ROS drivers for acquiring the measurements from the retroreflectometer using Bluetooth communications. So the main autonomous capability of the AMR will be the outdoor autonomous navigation. We followed two different approaches. We implemented two different approaches in the prototype. One was a 3D map-based localization, and the second one was a purely inertial plus GPS fusion navigation for both methods were meant to be tested in different environments. The first one was for GPS denied environments. The second approach was focused to test in environments where there were not really features like a highway where there are not anything in the sides of the road to make the lock of the localization. In both cases, we used off-the-shelf components that are available in the ROS development environment. We used LeoSAM for mapping. We used HDL localization for localization. This is an entity-based localization method for 3D maps. We used road localization for sensor fusion. And for the planning, we used the standard the navigation stack from ROS. But for achieving this 2D map from the 3D map we are using, we followed an approach in which we extracted the floor surface from the 3D map, and based on the normals of the floor, we defined, or we were able to identify the parts of the environment that the robot was able to reach or not. And we built this, what we call the transitability map, that is just does the occupancy grip that represents the areas of the environment that are reachable for the robot. So the second main autonomous capability was the ability to detect and align the robot with the road markings. So the retroreflectometer requires a quite accurate alignation with the road markings to get proper measurements. So to achieve this accurate alignment, we followed a visual surveying approach. We had one coaxial camera mounted just on top of the retroreflectometer, just capturing exactly what was in front of the reflectometer, and using just more or less standard machine vision techniques, we were able to detect the road markings and define a bounding box, which will provide us with the vector director vector of the road marking that will provide us the distance to the center of the image, that is the distance to the sensor, and the angle relative to the sensor. So with this angle and this distance, we fed a PID controller that will control the speed and the steering of the platform until the sensor is properly aligned with the road marking that we are going to measure. So the autonomous capabilities are managed within what we call the Flexbotic Execution Manager, the FEM. This is an internal development from Tecnalia. This system is responsible to execute the missions received from the digital twin, which are composed of a series of locations, the places where the markings are, and that we need to measure, that the robot needs to follow in a sequence. So this the missions that we received, we passed them, and with them we built a YAML file that records both the states and transition between states. And this with this we built an state machine that is used by the FEM to manage what is how the mission is going, and what action the robot needs to do in each moment as part of the mission. So this system also has a higher level state machine that it's actually going to control the not the mission itself, but how missions are received, also control the error handling and this everything that needs to be taken into account to make sure that the mission is actually being carried out successfully, and that we are ready to start a new mission and so on. So the integration with the digital twin was done just using MQTT communication over 4G. We defined a set of standardized messages that we want to be interchanges between digital twin and the AMR. As you see there, these messages include the definition of the missions sent to the robot, and the measurements and telemetry data that are going to be sent back to the digital twin. So here this diagram shows the overall system architecture. So here on the left side we have the hardware platform and the sensor, and there in the right side you have the digital twin and the higher level mission management. So here there in the middle, you have also the autonomous modules that use the sensor that comes from the data to build an environmental representation. This representation and the data from the sensors is used to localize the robot, to plan motions, and to generate driving commands that are sent to the drive-by-wire platform. Also, the FlexRobotic Execution Manager orchestrates all the behaviors. It receives missions from the digital twin, sends navigation goals, and triggers the road marking detection process, which itself commands the necessary alignment maneuvers. Also, the FlexRobotic Execution machines controls the lowering and rising of the retroreflectometer platform and triggers their measurements. And also we have one MQTT interface that it's constantly gathering information from the different modules of the robot about telemetry and retroreflectivity, and it's communicating all the data between the digital twin and the FlexRobotic Execution Manager. So this development was validated through several tests conducted at our facilities here in San Sebastian, as well as 2 other live demonstrators on real roads. The first small-scale integration test was carried out in a nearby town in Abadiño, where the town council allowed us to cut a small section of the secondary road, where we did some tests there in a real road environment. And the final demonstration that took place there in the highway near L'Aquila in Italy. So in all cases, the prototype successfully performed its task, navigation autonomously, using both navigation approaches, executing the missions received from the digital twin, and accurately measuring road markings retroreflectivity. Here on the videos below, but you can see some of examples of the AMR operating in Abadiño, there in the left side, and also in the highway in Italy, performing the various autonomous operations that they need to perform, like navigation, detecting the road marks, aligning the sensor with the road marks, taking the measurements, etc. So overall, we were very satisfied with the achieved results and the performance of the system. We look forward on being able to apply these technologies also in other environments. So this concludes my presentation. Thank you very much for your attention, and I will be happy to answer any questions. So thank you very much.
Thank you, Ivan. Thank you, Ivan, for your presentation. We can now move forward with the last presentation for the second technology, set of sharing. I would like to call on stage King Zhang from Olsing, Mathieu Lapinski also from Cboost. I don't know if you want to be all together on stage or if it's one after the other, and also Hélène Labois-Bourget. Again, sorry for my pronunciation. Okay, so that we can see all together the advancement in additive manufacturing, 3D printing. So the floor is yours.
Thank you, David. Hi, everyone. So my name is Ching. I'm from HOSIM, working as a lead engineer. I will walk you through the work we have done in BEEYONDERS project on additive manufacturing. Our major focus in additive manufacturing for BEEYONDERS project is to develop eco-engineered and also innovative design for Kson application to transform this traditional resource heavy and also worker-heavy technology to highly automated 3D printing technology with innovations on design, material, and the manufacturing strategy. Not only for a better geometry of the caisson, which will allow us to save material. Our focus is also on eco-engineer of a new generation of maritime caisson, which can make them eco-friendly. This is achieved by 2 pillars. First one is on habitation creating by 3D printing of a very complex geometry. Second is on material engineering to control the fertilizer releasing from the material and the material surface texture so that it's more friendly for microalgae development. The work is a collaborative work where we have assembled different players in the construction sector, where Acciona and Seaboost worked for the structure and ecological design. Cobalt worked on the 3D printing, additive manufacturing strategy. We also focused on the material development. KDO and Technalia focused on sensor development, and all this is in line with InfaPlan, which benchmark the traditional caisson with the 3D printable caisson under development. The geometric design iteration is done led by Acciona with participations of all the partners. We have gone through different iterations, transforming the traditional rectangular caisson to optimized geometry 3D printable caisson. We also added modular biowalls on the surface of the caisson to bring the bioreceptivity to the caisson. On material perspective, we also add some water drop openings inside the caisson so that we can save material. By all these iterations, we achieved a caisson per design where we have saved more than 40% of the construction material. And we completely eliminate any vertical steel bars for steel reinforcement. Here are some results where we calculated by finite element simulation that how this new geometric design perform in different loading conditions through caisson standing, floating, transport, and the sinking phase of caisson, where the hydrostatic pressure counts. We also calculated the load distribution under ultimate limited states, where the forces created by waves, such as pulls and the sucks, are calculated. This gives us some confidence on how the structure performs under its operational environment, and if the design is standable in such condition. Once the design is frozen, we move to the additive manufacturing strategy, where we specify the new generation of Cobalt XL board gantry system can be adaptable to the printing of the full size caisson. We determined accordingly important parameters such as the geometry of each layer and the interlayer time. How long will take for printing one layer? With those inputs, all the printing parameters has been calibrated accordingly, which is very important and as a key input to estimate the construction duration, because this is a major construction duration phase for this new caisson. As for material development, we have distinguishedly developed two materials, as you can see on this caisson design. One on structured material, where we focus on bringing a ductility to this material, and the major difficulty was to incorporate the steel macroscopic steel fibers into a 3D printable concrete, where pumping and extrusion can be problematic. We also developed a second material which has boosted bioreceptivity in order to be even more attractive on material perspective for the first colonization on the material. This slide summarize the key performance where we validated in lab condition on the structure material. Basically, the material shows adjustable workability, very good ductility, and a very stable long-term deformation properties such as very low creep. All the material parameters and performance are summarized in this table. On the development of bioreceptive material at lab scale, one of the innovation that we're proud of is to have developed this lab scale monitoring system, which allow us to monitor the biomass development on the surface of concrete sample. It's a non-invasive technique based on chlorical fluorescence, where we can calculate the biomass on the surface of a sample developed in aquatic condition. As we can see on this figure on the right on the bottom, we compared the reference concrete surface with the 3D printable material surface after 1 month submersion in lab condition. The biomass developed on the new material is significantly higher compared with the reference concrete. Once lab validation is done, we moved to the operational environment of this of those materials. So although this slide shows the 3D printing trials we have carried out for validating the material processing parameter and the in-situ material properties under different 3D printing conditions, we have varied the geometry of the printing layer. We also varied the temperature of printing, and all this material being printed in situ. We extracted samples from those structures and compared their performance in situ with what we obtained in lab. We also casted some samples with in situ with the same temperature and same kerning regime with which we will compare. So the first comparison is done basically to check the geometric impact. If we have a smaller sample casted in situ, how it performs with bigger samples. It's a very classical approach, and we found unsurprisingly, when the sample is smaller, you have a higher relative strength. And next task was to compare the samples extracted from different orientation of this 3D printed structure. We compared basically on the left, the samples cutted vertically from the 3D printed wall with those cutted horizontally, which we found that the material is anisotropic. Basically, you have a very good ductility along with the printing and extrusion direction, but vertically, the ductility is much less. Similar conclusion can be found when we test the samples in a different angle, always anisotropic. Once down on the material, we also wanted to check the structural factor. If we are printing more layers, if we test on a bigger element, the printing defaults may enter into account, where we tested different panels cut from 3D printed structure. The result is presented in this slide. And with the results, we basically gave design recommendations on structure level, which we consider that the material has about 3.2 or 3.0 MPa as tensile strength, which is taking into a relatively big safe margin compared with the material tested in lab condition. As for the in-situ performance of a bioreceptor material, we carried out 2 trials, and the major focus is to check the printability of curvature, which is necessary for this bio wall design, and also the openings that can be problematic to handle in 3D printing process. I'm now moving to the next part of the presentation, where we move from lab validation, in-situ validation, to a real environmental operational validation, where we start from on material trials. We have produced 25 tons of the key component in a 3D printable concrete in France. And we have instrumented a quality control plan in which only minor batch of the production shows some variabilities, but all the batch control has passed the limit of control, and showed that they can be used industrially. As for the demonstration of the casing itself, we split it into 2 parts. One part focusing on submersion of the bioreceptive wall of the caisson. Another part focusing on the structural performance of the critical part of the caisson, which has been developed. Well, I will start with the structural prototype design. Basically, the major objective is to check this optimized geometry of caisson, how it can bear loading and in a real condition. So we have a scale down the real scale design into small elements. So 5 repeats of these small elements have been produced by Cobalt last year, and 3 of them were tested in Technalia, with implementation of deformational sensors on the surface of the element. And the structure test result shows basically when we calculated what is needed for the structure design, we needed to achieve 15 tons of load on the structure tested. And as you can see on the figure on the right, all the 3 elements passed this limit. This is a very good news in a way that it gives us much more confidence that we don't really need vertical shear reinforcement, and the structure can perform relatively good in representative loading condition. Now I'm handing over the presentation to Mathieu from CBoost on the work done on bio walls. Mathieu, thank you.
Thank you, Ching. Can I recover you the remote? Thank you. So hi everyone. So yeah, my job at CBoost was to bring life to this construction. So everything we have tested in vitro or during the construction phase that you might know, and the 3D printers. Now the objective was to downscale this huge future caisson to prototype, to test it underwater. And of course, we have worked on the design and how improve the cavities, trying to get shelter, basically for fish, for octopus, whatever marine species you know or you heard about. We try to make a feasible design and also something that we can replicate. So not only one unit, but different replicates in order to be as much as we could significant and pertinent in what we were doing underwater. And at the end, we had this kind of biowalls, which is around 2 meters length and 60 meters high. So it's quite small comparing to a full caisson, but still. 5 units were built by Cobalt in Copenhagen, and Holcim has built also different small precast and also same kind of size, but normal concrete to have a reference and to make comparison underwater. So 5 normal standard concrete that we are using in the benchmark and the 3D ones that we immersed. And all these come to Gijón, Spain, with a truck. So finally we got authorization to make the immersion. So that was quite challenging part of the job, but we did it. And the maritime works were quite light. So it's quite small boats because we were able to use a crane to immerse all the units first on the seafloor. And then using scuba divers and buoys, it was feasible to position the units very precisely. And actually, I was thinking that we use a ROV also just to double check where the units were. So underwater ROV that we can pilot from the boats, and it's just a way also to limit the dives and to improve the security of divers. So we didn't mention it, but it was the case. So we think about how to test during this immersion phase the comparison between our biowalls, so the 3D printed one with the reference normal concrete units. And to do so, we lead different type of underwater protocols. Basically, the first one was to count the fish, scuba diving, and also we put cameras to try to understand if the effect of a human being diving could limit the results, because it's quite small in comparison to the small fish. And the unit is 2 meters length, so we wanted to know. And also we studied not only the fish and the octopus or whatever, so everything which is moving on the seafloor. We also study what was shown in the aquarium, so how the substrate is going to be colonized through the time. So to do so, we just take picture, always the same size, always the same at the same place, and during 2 campaigns, so one after 2 months, which was in summer, and one very recently after 9 months, which was in March. And we compare all the results in Gijón. So yeah, we also made this PAM. So the PAM we did in the labs, we did it underwater. So we have seen in these results that it was the same. It's a very conclusive result because during the first months of colonization, the biowalls materials is very efficient and you have more biomass, more photosynthetic activity of the very small algae you have during the first step of colonization on the materials used to make the biowalls. And also it's really impressive during the first step, especially in this picture here on the left, you can see that it's the same amount of time with the reference and with the 3D printing biowalls and bioreceptive concrete. And then it's after 9 months. So everything got colonized at the end, but it's way faster with the biowalls, and then we will see that in terms of composition and everything. It's also very interesting to see that after 9 months, and it's also, you have seen on the picture, but also after 9 months, what we call the bare substrate, so the concrete without nothing, is really less on the biowalls in comparison with the reference. So it means that you have more algae, more mollusk, bryozoa, whatever, sponges on the biowalls in comparison. So here you see the biowalls. It's a picture by the drones, by the UVCs, this one, during the immersion, and you see the difference about what is settled on the concrete, really. And these results are more about what is moving around, what is living around, so the fish, etc. all the colors are more about diversity, and the higher of the curves are more the number of fish, etc. And you can see that after only 1.5 months, which is really what we were talking on the corridor with someone, it's very fast as the colonization come very fast. You have a lot of fish, and on the biowalls you had up to 10 species. And 7 of these species were only seen on the biowalls. That's something interesting. And even during the Sangon campaign, so you have to note that we had more fish in terms of diversity and everything on the first campaign because it was spring. It was spring and summer. And here it was really winter. But even in winter, you have more fish on the biowalls, which is very interesting, depending on the campaign and the species. It's not something linear, but at each season, you have a significant effect of the design and the material. And we were talking about the species that really live inside the cavities. So we have the material, we have the design, we have the 3D printers, and the biowalls bring everything together. And we have 2 species, the very cutie octopus, which was only found inside the cavities of the biowalls. So it means that the reference or normal concrete like this, there is nothing to hide. So you see, you cannot have anything on it. You cannot have something living inside. So we had this proof of concept with the octopus, of course, living inside the cavities. And we also have this very cutie blenny, so the ring-necked blenny, which is a very shy small fish like this. And when you come over, it's always coming inside a crevice. It's very shy. And we had a very numerous number of these fish, like up to 10, 13 sometimes on one unit. And on the reference, nothing, because he has nothing to hide. And also this fish is eating small algae. So it means also that he has something to eat and not only something to hide. So that was mainly the most interesting result we had, but we will talk more, I think, about it tomorrow. So to conclude, Hélène from Holcim.
Thank you, Mathieu.
I'll take a word.
And I think you've seen that we have demonstrated through prototypes with sections of caisson that we match both the structural objectives and bioactive ones for this design. In case you will feel a little bit scared about the fact to disrupt the construction of this industry, we have also computed the possibility to add some rebars so that you have something which is closer to construction habits in this industry. The benefits have been demonstrated by the study highlighted by Sandra. Material efficiency, overall more than 40% of reduction in concrete and steel consumption, which is really massive, which results obviously in a lower carbon footprint, but also an economic advantage and a construction duration which is shorter than with traditional construction. So now what we wish is to go to the real industrialization step, to have a proof of concept at scale 1 with a real caisson that we can leverage this technology to build better with less. Thanks for your attention.
Thank you, Hélène, and thank you, Mathieu and King, for your 3 presentation. And with this one, I think we close the second technology session of the day, and we are open for any Q&A concerning what we just saw concerning both the aerial and ground vehicles, as well as the 3D printing and additive manufacturing. So again, if any of you here have questions, or from people at home, this is the moment for you to, speak out loud. Also because we have to have some time to arrange the table there. So, sure.
I have a question. First of all, congrats, because this is really amazing, like mind-blowing. And I lost her. I had a question about, okay, there you are. So when you said it's autonomous, does it know that you have, the question would be, can it work with more people? Can there be people on the tunnel, or should everybody go out in order for the vehicle to be able to work?
the autonomous system already considers also the presence of different objects, entities, or people, in this case, around the machine. And for this, we have developed also different protocols, how to act depending on.
So doesn't kill anyone.
So in the case of people, for example, we decided that we just should stop the machine. In the use case, as it was just a prototype and very few time to test everything, we didn't consider the presence of people inside of the tunnel. Basically, also because there was not enough space for the people to be inside the tunnel at the same time of the machine. But yes, it could be considered.
And so if the tunnel was bigger, could you do a protocol in order to, have more than one unit and they could cross each other? Could that be done?
Yeah, that could be done. In that case, that could be for the next project, because there are the issues regarding cooperation between machines, so they could share the information between each machine. So to share the information of what the machine that was in the excavation front has seen. So when it crosses the other one, it can communicate how the excavation front was left, for example, to plan better the next operation. That could be done and could be very interesting.
Thank you very much. And congratulations again to everyone.
Thank you. I don't know if there are any more questions from the people here. I've been told that people from home didn't write. Okay, that's fine. So if there are no more questions, I think we can move forward with the panel discussion with representative of both the Beyonders and InCube project. We have Eva Martinez-Cruz, expert social innovation. We have Sofia Finzi-Longo. We have Arshita Takare. We have, sorry, again for the surname, I hope I didn't pronounce it badly. And we have Maria Teresa Lazzaro. And so we will delve a bit deeper into a white paper that has been written about how technologies developed both by Beyonders, InCube, and many other projects of the Tech4EU construction cluster can contribute actively to, solving the issue of gender imbalance within the construction sector. So I will give the floor to all of you, just giving you the microphone.
So good morning, everyone. I hope you still have some energy. I know this is the last session of today, but we hope it's going to be interesting. So welcome to our panel session, which will be focusing and discussing whether emerging technologies can make construction more inclusive. So my name is Sofia Finzi, as Davide has said. I'm head of impact acceleration at Icons. I will be introducing our panelists shortly. So what is this panel about? We have said already during this whole morning that construction is undergoing a major transformation, right, which is driven by automation, robotics, AI, and also digital technologies. But at the same time, we have seen that the sector still faces important challenges, which are related mostly to inclusion, diversity, and particularly regarding women's participation. So within the Tech4EU construction cluster, which brings together different projects, including Beyonders, InCube, Robert Armé, and Human Tech, a study was launched, and the objective was to explore together a key question, which is the one that we have put here. So can emerging technologies help address gender-related barriers and also contribute to making the construction sector more inclusive? This is the core question of today's session. So the findings of the white paper are quite promising, but they are also nuanced. So the white paper on one side shows that technologies can on one side reduce the physical strain, as you have seen, improve safety, but also create more technical and skill-based roles. But at the same time, we have seen that it highlights important tensions. These technologies can improve working conditions on one side, reshape tasks, but the main barriers to women's participation are, emerging technology can improve working conditions, but the main barriers to women's participation are still perceived to be cultural, okay? So stereotypes, unwritten norms, and the perception of those people who belong in construction. So today, what we'll be exploring are the main findings of this white paper, and we will be discussing the role that emerging technologies may play in fostering a more inclusive construction sector, based on the perceptions and of the experiences of the professionals who are working across the sector in Europe. So at this point, I'd like to introduce our panel. Here on my left, we have Eva Martinez Cruz, social innovation expert at Icons Innovation Strategies, representing the BEEYONDERS project. Then we have Harshita Takare from Lama Social Enterprise, research and evaluation officer, representing the InCube project. And then we have Maria Teresa Lázaro from ITA, Instituto Tecnológico de Aragón, research and innovation engineer in robotics, representing the BEEYONDERS project. So before starting with the questions to our panel, I would like to ask everyone a question, which is, so when you think about construction work, what image comes to your mind? Is it physical labor? Is it advanced technology, or both? So if I had to reply to this question, I would say that before getting to know BEEYONDERS and the other projects represented in this panel, I would have thought about more physical labor. I didn't think about technology when thinking about the construction sector. But now, after getting to know the BEEYONDERS, InCube, and all of the projects represented here, I can say that I have finally seen and understood the great potential there is in terms of technology application in the sector. And this is clearly visible by all of the presentations that were delivered today. So as a first question, I would like to focus on why this paper was written. Eva, I would start with you. So the white paper was developed, as I was saying before, within the Tech for EU construction cluster. So what was the starting point of the work?
Thank you for the introduction, Sophia. It really all started with a shared objective across the sister projects, BEEYONDERS, InCube, Human Tech, and Rovetarme. So beyond the technological development that all these projects focus on, there was a shared interest in understanding the implications of these technologies in making the construction sector more inclusive, specifically inequalities linked to gender. Beyond this shared objective, there was also a shared challenge because, as we said this morning, there aren't many women working in the sector. So even if there were many pilots in all the projects, demonstrators, etc., we thought, okay, how can we reach as many women as possible? So we then came together with this initiative, making or taking advantage of all the projects and networks. So we developed a survey. We developed a survey to gather responses from professionals in the sector across all the project networks in Europe. And we managed to reach around 100 professionals, most of them women. Our questionnaire actually present them all the technologies and ask them questions related to what they think, how they think these technologies can help the construction sectors in terms of inclusivity, etc. And so, yes, I will say that this is how all started.
Thank you, Eva. And also, the paper suggests that Construction 4.0 is not only a technical transition, but also an opportunity to rethink participation in the sector. So what does that mean in practice?
Yes, so construction traditionally has been linked to heavy manual labor and also with masculinized work cultures. So what we are seeing now with the emergence of all these technologies and the introduction of these technologies in the sector is a gradual shift towards a more technical and digital type of roles, right? So all these technologies are changing what I would say the nature of the work itself. So, and this is creating new roles, new opportunities also to broaden who can participate in the sector. But there's always a but. With new opportunities, also new challenges, come in. And this is related to how organizations also evolve with the introduction of these technologies.
Thank you, Eva. And Harshita, from your perspective, what is the most important message of this white paper that you have jointly written?
Okay. First of all, thank you for the introduction and also for all the presentation. It has been super interesting, and I would like to congratulate you all for the results of your project. So for me, the most important message from the paper is, as you said already, that these technologies can improve entry and working conditions for the sector, but they do not guarantee inclusion itself. So as Sophia highlighted earlier, they can improve safety, well-being, reduce physical strain, and more importantly, they're changing the nature of work. So how certain tasks are performed, especially on the construction site. So they are creating new opportunities or new kind of roles within the sector. And for me, what's important is the distinction between creating these opportunities, but also ensuring equal access to these opportunities. So I think it's really important that underrepresented groups, or especially women, have equal access to these new emerging opportunities, and also to the decision-making spaces that are linked to these opportunities. So overall, these technologies for sure can support inclusion, but only if they are governed or implemented with the objective of inclusion in mind.
And was there a finding that surprised you or that challenged the way that you believe we usually talk about gender equality in construction?
I would say it wasn't super surprising, because the impact of the technologies that we discuss in the white paper were quite in line with the literature that we investigated. But as you were mentioning before, that when we talk about women's entry to the sector, one of the key barriers that was highlighted by the respondents was cultural issues. So when we asked the respondents more generally, according to them, what is the main challenge for the sector, they often said, okay, maybe there is lack of flexibility, there is a low work-life balance in the sector. But when we made the question specifically for women's participation, it was always the cultural issues. And what stood out personally for me was the qualitative feedback that we received from a lot of female respondents, that they described very concretely the type of exclusion they've been facing within their professional lives. So I think that was quite striking for me. I can make some examples, like a lot of recurring themes were related to biases that they face during the recruitment practices. So a lot of them being asked about their family plans, or a lot of them said that they had to persistently prove their credibility within the male-dominated environment. So these were quite recurring themes that emerged. And I think these are particularly important because when we say cultural issues, they are not something abstract. Let's say through the paper, we found that these are really experienced by the women working in the sector quite practically in everyday manner. So, yeah.
Thanks, Harshita. What I forgot to mention is that Eva and Harshita are the lead authors of this white paper also, so that's why they are here today. So at this point, I would like to move to the second block of this discussion, which is what barriers are we really trying to address? So Eva, I'm going back to you. The white paper distinguishes between cultural, organizational, and structural barriers. So could you briefly explain these three categories and which of the barriers appear most relevant when we talk about women's participation in construction?
Yes, so we use these three dimensions because, I mean, we build on the literature, right? So we try to actually categorize the responses we got, and we needed some sort of understanding of how the architecture behind the inequalities in the sector. So we try to categorize all the responses gathered from our respondents into structural, organizational, and cultural barriers. Structural barriers is what we mean. I mean, they are linked to broader systemic conditions, like how we access the sectors, so education and work conditions of the sector itself. The organizational dimension it's more related to the organization themselves, right? So linked to work-life balance policies, career opportunities, training within organizations, etc. And then cultural barriers, and I think that we've already mentioned these, they are linked to stereotypes more at the societal level, not non-written norms, and how we as our collective understanding of the sector. And what was interesting is that when we were analyzing the findings, most of the respondents, where they were asked about the challenges without even focusing on the gender aspect, the challenges that they would find in their work careers, most of these challenges were linked to structural or organizational aspects. And then when we asked them specifically about gender inequalities and inclusivity in the sector, most of the responses point to the cultural dimension, right? So the perception is the issue is not about whether women or other type of underrepresented groups can do the work, but whether we think and they also think that can do the work.
And how do you interpret this difference?
Okay, so I think that, and this is one of the most important findings on the paper, because it suggests that improving working conditions for these groups alone is not enough. We also need to think about how to impact, let's say, the cultural dimension of the construction sector. What we've seen, and I think that we've been discussing this morning, is that technologies are very good at addressing aspects related to safety, automation, etc. But there is still the need to deal with the dimension that these technologies touches the least, which is the cultural aspect.
Okay, thank you, Eva.
Sorry. So I think that this is the kind of tension result that we found. So this is important to highlight this.
Thank you for highlighting this, Eva. Harshita, the paper introduces the idea of physical threshold, right? So physical strength and physical demands as a visible barrier, but also a possible entry point for technological change. Why is this concept actually useful?
So yeah, in the paper, we talk about the concept of physical threshold. So I think it's really useful because it's one of the most visible ways in which exclusion is produced within the construction sector. So just to clarify that we're not suggesting that women cannot perform the same physically demanding tasks within the sector as male workers. Rather, sometimes physical strength, or often, it's associated as a marker of legitimacy within the sector. So it really influences who belongs to the sector or who is competent for certain kinds of roles in the sector, especially if we talk about the construction site or the roles linked to construction site. So when we were doing the analysis, so it really made us think like how these technologies are changing certain roles or the nature of work around these roles, but also importantly, understanding how these roles are perceived within the sector. So if we talk about technologies linked to robotics, for example, or exoskeletons, I think they really have a potential to contribute in a way to reduce this symbolic importance that is attached to the physical strength to certain tasks within the sector. So they can, I think, in a way, help reshape that image. But again, I want to point that the concept of physical threshold should be considered as one of the entry point within the wider inclusion sector, within the wider inclusion strategy for the sector. So it's one of the entry points for the women.
So one question comes automatically. Is there a risk that by focusing only on physical demands, we oversimplify the issue, since in fact there are many barriers which are actually related to stereotypes, that we were saying before, work site culture, and also informal practices?
Yes, absolutely. Like one of the cross-cutting finding across all the technologies was, okay, these technologies can support safety, they can improve working conditions, but if we don't address the cultural barriers within the sector, there will be no true inclusion within the sector. So if we focus only on the physical aspect or the physical threshold, then maybe we risk oversimplifying the issue of gender inequality within the sector and maybe consider it more as a, let's say, technical design issue, but that's not the case. The true barriers really are associated with improving or making inclusive the workplace culture, the recruitment practices, or ensuring equal access to training and skill development opportunities for all. So in a way, these technologies can redefine the nature of work, but they cannot they cannot change how certain tasks are perceived within the sector. So they cannot change the meaning attached to certain works within the sector.
Thank you, Arshita. So heading towards a more practical aspect, I have a question for Maite. So Maite, from a technical perspective, when autonomous machines or aerial robots are introduced on construction sites, which types of tasks or risks are they most likely to change on the work site?
Yes, well, I think we've seen several presentations today regarding to this. I think the type of tasks that are going to change are tasks that are repetitive, that imply physical interaction with the machine or the different systems, tasks that involve some risk to the human, like what we saw before regarding the machine entering in the tunnel where we have this dusty atmosphere, no, which is unsafe for humans. So, well, yes, in general, we will reduce certain risks in the construction site regarding collisions, the risks due to, for example, low visibility conditions or due to the fatigue in the workers.
And do these systems might mainly reduce physical exposure and safety risk, or do they also change the way that the human role is needed on site?
Well, I think they do both. The main goal is, of course, to reduce the risks and to improve the safety of the workplace. But at the same time, it's going to change the type of roles that are needed in the workplace, especially roles related to supervision, monitoring, planning the mission for the machines, to understand where the machine has to be at some point in time during the day. So all these new roles will appear and I think it will create a broader range of people that could participate also in the workplace.
So let's dive a bit deeper into the technology, Maite. So we have talked about the barriers and about the idea that technologies can modify some of the physical and organizational conditions of the construction work. So now let's try and make this a bit more concrete. So we were saying, you have seen from Maite's presentation before that ITA is developing perception, mapping, and navigation systems for autonomous machines within the BEEYONDERS project. And this includes aerial robots and autonomous wheel loader. And these were tested in a tunnel scenario and an open world construction site. So Maite, could you explain in accessible terms what a perception, mapping, and navigation system is and does for autonomous machines and on a construction site?
Yeah, so basically these are the different modules that composed a whole autonomous system traditionally. These different modules allow the system to understand its surroundings, to understand where it is, and how to move safely in the environment. No, so for example, we have perception systems that rely on sensors, LiDAR, cameras, radar, depending on the situation or on the specific task that we want to address. Then we have localization and mapping systems that allow the system to understand its environment and where it is positioned within it. For this, we can use different map-based algorithms, as what we have seen in some of the presentations. Also, we could use GPS if it is available in outdoor scenarios. And with this information, we have then the navigation system, which is in charge of computing trajectories for the machine from its current position to the destination goal. So, and to plan trajectories and then execute them, taking into account all the perceived environment during the execution, just to know if it has to adapt the trajectory to, for example, some obstacle present in the scenario.
And what does the machine need to perceive, map, or understand the environment to move safely?
Yeah, so basically, regarding the perception system, the machine should have, well, it should cover with its own sensors, like 360 degrees perception around the machine, so it can move and maneuver safely in the free space. Apart from that, with the perception system and AI-based perception algorithms, we can identify different entities in the scenario, other people, workers, obstacles, other machines. And then what we use are different tracking algorithms that allows the machine to understand, well, estimate the position of the subject and let's say the distance, for example, to the machine, the relative distance, and also the velocity. And with this information, the navigation system could act differently depending on the type of object. No, the machine could decide that if there is an obstacle that doesn't suppose any risk, the machine could simply try to avoid the obstacle, to replan its trajectory to avoid it. But for example, it could decide that if there is a person in the surroundings, in a delimited area of security area around the machine could simply decide to stop. No.
And within this scenario that you are describing, where is the human worker in relation to the autonomous system? So are they operating, supervising, validating, intervening, or interpreting data? What are they doing?
Yeah, so when we are introducing autonomous systems, the role changes from the perspective of the operator. We just, so it shifts from the manual operation to other tasks related to supervision, monitoring, understanding the data that the autonomous system is generated. And well, in the near future, what we are going to see is workers commanding remotely the machines. This is going to be the next step, to have a remote control of the machines. So, for example, in the case of the tunnel, the worker could be monitoring from outside the tunnel, controlling remotely what is happening inside. Yeah, this is what we will see soon. Workers commanding from their offices several machines in parallel, probably placed in different parts of the world simultaneously, thanks to 4G, 5G communication. And what we are also seeing is that manufacturers are starting to design machines without cabin. So they are envisioning that the human is in a safer position if it's not physically interacting with the machine.
So basically, you are saying that this will change a bit the skills that are needed on site. So this could maybe create a shift that will create new roles, as you were saying, around supervision, remote operation, or data interpretation, maintenance, or safety monitoring, for example.
Yeah, so the type of skills that will be required will change from physical skills to technical skills, understanding the technology, understanding the data that the system is producing, be able to interpreting the data. In general, the usage of digital tools, how to use human-machine interfaces. Yeah, I think physical interaction will be still needed, but I think it will be more focused only in maintenance tasks when you have to do some supervision or reparation on physically on the machine.
Thank you, Maite, for this very concrete overview. Going back to Eva, so listening to Maite's example of the work carried out at ITA, where do you see the strongest inclusion potential? So is it about reducing the exposure to hazardous environments, for example, or creating more technical roles, or also changing the perception of construction work?
So I think that the strongest potential actually comes from the combination of the three aspects that you just mentioned, because reducing the exposure to hazardous or physically demanding environments is very important, because it changes directly some of the most, let's say, difficult barriers to tackle, which were this strong and very demanding physical interaction. But I think, and we said before that, of course, technologies have not at the moment the potential to deal with the cultural dimension. But with this opportunity of new roles emerging, new ways of understanding how work is organized, I think that there is also this potential under the right circumstances, of course. There is this symbolic dimension in which these new roles, these new technologies can help modify how we imagine the construction sector, and eventually, support also the change in the cultural dimension that we need.
So actually what the white paper says is that autonomous and teleoperated systems are perceived positively exactly because they can shift to work towards more technical and specialized roles, right? So could you provide us a bit more detail on how the respondents to the survey you have shared perceived the autonomous and also the teleoperated systems?
Yes, so most of the respondents actually, they perceive this new change or this new introduction of more technical roles evolving from more, from being physically demanding to monitoring, data interpretation, etc. And this was really appreciated by the respondents, not only with these autonomous vehicles, but also with the other technologies. But there was also this aspect that was linked to this opportunity of new roles emerging in the sector, which was that people think, and respondents think, that they need to be accompanied by equitable access to these new roles. So through digital upskilling, trainings, etc. So what we actually acknowledge in the paper is that investment in new technologies, it's very important, but it needs to be together with how organizations organize themselves around training, etc., and opportunities for these new ways of accessing roles and how to manage these new technologies.
Thank you, Eva. Starting from what you said, here comes a difficult question for Harshita. So from a human-centered perspective, what should we pay attention to when we want to introduce new technologies into a construction site?
Okay. I think from the human-centered perspective, the key question will be who is benefiting from these technology and under what conditions. So it's really about the end user. So it's really about the workers who are going to adopt these technologies. So it's really important they understand correctly and clearly the purpose of these technologies. And it's important that they trust these technologies, and if they have confidence and skills to use it properly. And I think this becomes especially important when we talk about monitoring related technologies. So in our paper, we discuss about a PPE monitoring system, wearables, and I think this question was also raised earlier before. And some of the key findings that we've linked to these technologies was the user acceptance could be low because the workers often associate these technology as surveillance tools. So they think that their performance is being monitored through this task, and really in some cases the user acceptance was low because they think they are being monitored and so on. So it's really important that they really understand the purpose of the technology very clearly and how it's going to benefit them.
And how do we make sure that the workers actually trust this system, these technologies? And also, how do we avoid a situation where only already privileged workers get access to the training that these new roles need?
I think for the first point, it's really important to be transparent. And second is about user engagement. So I'll be repeating myself, but again, it's really clearly communicating the purpose of the technology to the end users. So they need to understand how even the data that is being collected through the technology will be used or protected, and how it's going to eventually benefit them or improve their safety or well-being eventually. So that needs to be super clear in the first place. And second is about user engagement. So it's important while you are prototyping or testing this technology, you need to engage the user, collect their feedback, understand how they feel with its adoption. And also there is a need to identify user needs related to different technologies. So if you're talking about exoskeletons or wearables, there might be different user needs based on different body types, for example. So it's important that these are taken into consideration in the final implementation of these technologies. And related to the second point, I think in order to make sure that there is equal access to training opportunities, there is a need to move away from informal practices or informal access points, let's say. So it's really important for the new technology providers or construction companies to have a clear targeted strategy, outreach strategy, that also takes into consideration diverse profile linked to these new technologies, because maybe there are a lot of people who could be interested in automation or these kinds of tools and technologies. So it's important that they have inclusive and clear criteria for skill development related to these technologies.
Thank you, Ashita. So at this point, heading towards the end of our discussion, I'd like to move to a more practical aspect, right? So we have seen that the white paper shows that technologies alone will not automatically change the construction sector. They will not make it more inclusive per se. So the impact will depend on how these technologies are implemented, how people are trained, that's what you were saying, and how organizations adapt based on around those technologies. So for this part of the discussion, I would like us to focus more on solutions and practical actions. So I'd like to ask a question to Eva. So again, according to the white paper, so what should construction companies do to ensure that the technological transformation also leads to a greater inclusion?
Yeah, this is a very difficult question, and I don't think it's a straightforward one. But yes, I mean, we've seen that technologies alone cannot bring greater inclusion. But I think that what companies need to understand is that an integrated approach is needed. Okay, so investment in new technologies, etc., but also investment in training, access to decision-making processes for broader or underrepresented groups, etc. And I think there is another aspect linked to the these new technical roles that these technologies are helping to create, which is visibility and the access to these roles. So it's about if we want to get more concrete, and it's not an easy thing to do, but how we develop also targeted strategies to reach those groups that could, the new entrants, the future entrants to the sector, that they are aware of these new technical roles and the possibilities that they can bring for them to enter into the sector that perhaps before would be completely banned. So I think that companies need to focus also on this visibility aspect and providing greater information of all the technologies that they are adopting.
So basically what you're saying, that it's not just about introducing these new technologies, but it's also about changing the work environment, so the workplace practices.
Exactly. It's about, and I think that I already answered to this question. So it's about changing the whole workplace culture. It's about adopting an integrated approach, which is not easy. There is still a lot of awareness linked to this. So it's really about integrating the new technologies and also how we make them accessible in a very inclusive way.
Thank you, Eva. Another important point which is mentioned in the white paper is about changing the perceptions of the sector. So could you tell us a bit about why it is important that these perceptions change?
I think it's really important how people, especially younger generation, perceive construction sector itself, because the career choices, they are made long before people enter into the labor market. And often we have heard, like when we talk about construction sector, it's often associated with terms like physically demanding, unsafe, and especially if we talk about construction sites, something like dirty, dangerous, and often male dominated. So I think that can deter a lot of people to enter into the market. And as we were saying, that these new emerging technologies based on robotics, based on drones, they can contribute in shaping a little bit the image of the sector. I mean, it's evolving the sector, but there is a need to also communicate that these type of career roles are available in the sector. So again, it cannot be just a communication exercise, let's say. There is a need to make these make visible examples of women or other professionals that are working with these kinds of technologies, and again, providing real training opportunities linked to these emerging roles that are linked to digitalization or robotics.
Thank you, Shita. And introducing another topic, which is the how younger generations perceive the construction sector. Do you think that these technologies can actually help change the young generation's perception of the construction sector and the construction careers?
Yeah, as I said, like to a certain extent. And also this is something we found out in our survey findings, that these could be a more appealing career option for younger generation. But I think there is a need to better investigate these, whether younger generation truly consider them as a viable career roles. And for this to happen, I think it's really important that these kind of emerging roles are being integrated and introduced early on within the career pathways already. So within the schools, within the vocational educational systems, or within the career guidance in general, to understand whether they think this is something that they can go forward with.
Thank you, Shita. And I have a last question for Maite. What does it mean on a developer's perspective to have an inclusive technology design? What does it mean in practice?
Well, yeah, from the developer's perspective, I think, well, the technology should do, of course, should solve the task it has been designed for, but at the same time, we should be sure that the technology can be usable, understandable, and accessible for people in general, the average user. This means to design, for example, intuitive interfaces to interact with the different systems. I don't know, people, for example, I was just also thinking on the exoskeletons. People come in different sizes, anatomies, or regarding user interfaces. People has different intellectual or technical capabilities, and we should take all this into account during the design process from the beginning, I think.
Thank you, Maite. So I have one last question for all of you. So, which is, if you had to choose one action that you had to make to to make the technological transformation happen and to make it more inclusive, especially. So what would it be? Starting with Eva, 30 seconds answer if you can.
Yes, so I think that my priority would be to strengthen how the gender dimension is both requested and assessed in procurement frameworks. And let me explain this just very briefly. So, in projects, tenders, etc., it's already requested. All the technological development needs to include have this more inclusive dimension in it. But I think that what we are lacking is a shared understanding of what really means in practice to develop a new technology that is inclusive, and also how we evaluate whether it's inclusive enough. And we've seen this in our projects. So, yes.
Okay, I will keep it super short. I think I've said it a lot, but for me, it's about creating equal access to training and skill development opportunities to linked to these new emerging roles in the sector.
Yeah. For me, I think that technology is starting to reach a readiness level. We've seen this in Beyonders. I think that the next step is to involve the user in the design process from the beginning, just to allow that the technology is usable and accessible for all people. Otherwise, I think instead of reducing barriers, we will increase barriers due to the technological gap.
Thank you, everyone, for your answers. So if we had to wrap up a bit what was said, a lot was said, actually, but so we have seen what emerges from the discussion is basically that technologies can actually help reshape the construction work, okay? So they reduce physical strain, they improve safety, and they create more technical and skill-based roles. But also on the other side, we have seen that inclusion is not driven by technology itself. So these cultural barriers we were talking about, these remain central. So real change depends on how the technologies are designed, as Maite was saying, how they are implemented, how they are supported through training, organizational practices, and in general, broader efforts to reshape the perceptions of the sector. So the challenge is not only transforming how construction work is done, but also who feels they belong in the sector, in the future of the sector. So at this point, I would like to thank our panelists for being here. I would like to thank everyone for attending this last session and invite you to download the paper via the QR code, which is visible behind us. And a last thank you is for our coordinators who made this work possible. So thank you very much. And of course, if you have questions, this is the moment. Davide.
Just have one question, which maybe is sort of a wider one. I'm not sure we might tackle it here, but we spoke so much about the topic of stereotypes, and we are so focused on the technical aspect. But I don't know if it's actually a question, but I think that one of the elements on which we should try to focus a lot is also on the narrative overall, that encompass the way we also, teach children about stuff. I remember when you were saying, like, dirty is one of the words that are usually associated with working environment. I cannot think, I think also of the work of the Professor Jochen, but sometimes it was mentioning also the way of the importance of teaching children, teaching younger generation from early on how we should tackle the topic of safetiness, and especially maybe at this point, not just safetiness, but also, gender balance, respect of not just gender, but also like those groups that are minorities or with physical element of difference somehow. So still, I think that maybe we should also try to imagine that our own effort should move outside of the topic of purely construction, technical people, technical jargon, and move directly into the day-to-day life. So again, not maybe a question, but a sort of reflection that I pop up to my mind on top of what you just said. So thank you.
Thank you, Davide. No, absolutely. I think that this is, of course, a conversation that would be taken outside, all the great work that all these projects have done. And this, I think that we have a responsibility as a society to actually make all these changes when it comes to the new generations. And I think that in our, small spaces, we can start doing these things. Now we were talking about, of course, this will not change anything, but we can start doing something like targeted communication strategies to show what these new technologies can bring into the sector. And I think it will be also a narrative that probably, and this is an assumption, a big assumption, but will come with time. So as the more these technologies get into the sector, the experiences also of workers will change, so also their narrative. So my 2 cents.
I think that covers everything, but it's an important point, of course. And in the paper also, we talk about this in the structural barriers, like the stereotypes, they are really there, and how people perceive their career choices are linked to it. So it's important that we try to be a bit neutral when we talk about certain tasks or works or in general within the field. So it's important that early on in the education, it's taken into consideration, of course.
Thank you very much. I don't know if there are any more questions from the people here. If not, I think we can also thank you all once again of the importance also of your speech you just gave. Also by simply looking at the room in which we are, I'm happy to see faces of female women, giving us this important speech. And we see that, most of us are technical people. We see an imbalance immediately here in the room. So we see that there is quite a lot of work to be done in this sense. So I think it's a major topic, the one that you just shared. So I think that with this session here, we wrap up today's event. Again, I would like to thank you all very much for, travel here, attending it. And if you are online, for spending your time together with us, it is much appreciated. We are very happy to share what we've just done in those 4 years with the whole set of you. Actually, I would also like to invite you to the lunch, which will be outside of this room. I don't know if I maybe want to ask also Antonio to share a couple of final insights as a sort of wrap up of today, because maybe we have a sort of farewell after this lunch, but I think maybe people will also go if you want just to give us a 1-minute speech. Maybe not. Yeah, it's fine.
Well, regarding this panel, I have to say I started working here, well, a lot of years. I don't want to say how many, but when I started, both women and men were very different. Here, men were more rude, and women more inexistent. And today I have to say that if you have the opportunity to walk around of this company, you will see a lot of men, women integrated, working together, and these kind of things that we have talked here are being a reality. So I think there is hope, and these kind of projects and this kind of panels and these kind of initiatives are having success. So thank you.
Okay, thank you very much. Have a good day. Yeah. I think we can go to a... Yeah, indeed. It's time. Come on. Up. And the people at home, thank you again for attending. We will share an email with the various recap of today's activities and also with the white paper from Social Innovation People, Icons, InCube, and the Tech for Edu Construction cluster. Thank you.